Um, first one. All right.
So the female, did you get the blood type is II,
Yeah.
and then little r, both recessives for R, then MN,
Yeah.
and then A type blood with I, little I,
Yep.
and then heterozygous again, then MN. Okay.
Yeah. And then the child was homozygous recessive, and then it should be
Homozygous.
homozygous
I don't know if
dominant.
it's dominant.
They're both dominant.
Yeah,
so
so homozygous
just M. Yeah.
Yeah. Okay. Then the second one, did you get 1 out of 32?
Yeah.
Okay. And then 3 out of 80 is what I think I ended up with.
3 out of 80.
Yeah, unless I did my math wrong, which is entirely possible. IBI.
I got 1 out of 64.
But yeah, looking at it, A doesn't make sense. Out of 80.
So you get 1/4 on all of them. 1/4.
Well, but the genotype of that, because where was I?
Here are the Punnett squares.
Yeah.
So this is the male on the top and the female on the bottom. So you got B as the male.
Yep.
And then you got a recessive
Yeah.
A with the recessive.
With the recessive.
You get 1/4 AB, 1/4 A, 1/4 B, 1/4 recessive.
Yeah.
And
Yep,
then heterozygous for both.
One portion of a child born to a man with that genotype, and a woman with that genotype have blood types B. So you'd have to have, given their types, you'd have to have an I, those, and then R minus is recessive on both. That's where I messed it up. I was doing that they'd be R positive, not R minus.
You're
So
looking at
I think I looked at
this one. We're down here.
Oh yeah, you're right.
So R heterozygous RR, heterozygous RR.
Because wouldn't the R positive, wouldn't both big R and little r and RR both give you the RH plus?
No, it's just the
Oh,
big
it's
R, big
only
R.
the dominant. You're right. So I just misread that. So it would just be 1 out of 64, right?
Yeah.
Because everything's just 1/4. Yeah, you're right. And that was me misreading up there, but okay, that makes sense. And then the last one, the man can be, right? Is what I think I ended up with, because he's got a dominant B with a recessive blood type.
You said he said yes.
Yes.
I put no
Okay.
because
What did you?
The mom and dad can be both. It can be heterozygous for both blood types.
Okay.
Except the dad would have to be big N to be just N. Because you can't have, it's codominant, so it's M, N.
Yeah.
And then it would still work out for the mom because the mom has to be heterozygous, so it'd be MN.
Yeah.
So.
But doesn't it say that the father does have the man with blood types B, R plus, and N? So isn't he already NN? Because he's not an MN. He's not an MN. He's not an M, so he'd have to be a homozygous N.
Yeah, so he's got homozygous N.
Yep.
And she's got heterozygous MN.
Yep.
And the kid is MN.
So with her M and his N, 50% of them would be MN. So it's possible. I mean, there's no guarantee that he still is, but it's at least possible is what I figured.
Yeah. So he's saying that he's not the father.
Yep.
So it is possible, which means that he's not correct.
Okay, I guess you're right. So it's a double negative. But yeah, so he can't be, he could be a father.
He could be the father, yes.
Yes. Yeah, and that's what I ended up with, the same answer there.
Okay.
So then the second one, the first one I didn't get. I couldn't figure out how those two worked together.
Okay.
And I was trying a bunch of different things, and I could never figure it out.
Okay, so the walnut, it says in the homework that they have to be at least dominant for one allele. At least dominant. Both genes have to have one dominant.
Yeah, so you have to have at least one dominant.
One there and one there.
Yep.
Rose is
dominant
R,
and then little p's.
Yeah.
and recessive P's.
Mm-hmm.
And then P,
It's little r, P,
and it has to have a dominant P.
P. Yeah.
And then single, it's got to be
gonna have
recessive
that,
for
yeah.
both of them.
Mm-hmm.
Yeah. And then, so how did you figure out your Punnett squares to figure out what the parents could be on?
So you've got all these in a row.
Okay.
So you have to figure out what's going to get you to fill out each of these.
Yeah.
So if you put a big R, big P, you're going to get double R, and you can't have the P there because it's already filled. So what you do is you R and a little P. And you get big R.
Big R, little r, big P, little P.
Mm-hmm.
Okay.
Big R, little r. You don't do anything with the P.
Yeah. But the P would fill those both in.
Yeah, it would fill it in. And then little r.
Okay. I like how you did that. I didn't even think about doing it that way. So you'd have to have, you decided it'd be, so then how do you figure out what your parents would be? You'd have one that'd be RP, both recessive, right? And then your other one would just be the other.
Did I do that? Big R, little.
So I mean, I like how you're doing it this way, and that makes sense.
I'm
but
trying
then
to
how
find
do you figure out
the parents?
The parents' actual genes.
I'm trying to figure out how I did it. That might work.
This is number 2.
2A. I think honestly, I just guessed.
Really?
Yeah.
But does it end up working out for you?
Yeah. So big R, little r, big P, little P.
And then I think you were saying it was then a homozygous recessive on both of them, on the other parent.
Yeah.
Little r, little p, little p.
Mm-hmm.
Okay. And that's how I was doing all the rest of it. I was just making Punnett squares essentially, and filling in, trying to figure out what would work where.
I remember how I did it.
Okay.
So to get this, you do FOIL.
Okay.
So R, P, R, P, R, P.
Yep.
And so, and then this whole side, you got to use your R, little P.
Okay.
So this is essentially going to be little R, P, P.
Okay.
And so you just times those, and those are your parents.
Got it. Okay.
Yeah.
That makes sense. So in the second one, the 3 rows in a singular.
Okay. So 3 rows in a singular, which is going to be R, little p,
Mm-hmm.
and then a singular is R, R, P, P.
So we have a heterozygous R and then a homozygous recessive P times and then it's just doubled. So you'd have a little r here, and it'd be those two together, and it'd be this squared essentially. Together would give you 3 rows as in a single. No, I did it down here. Because with the recessive P's, it cuts you out of, you can't get a P anymore, and you can't get a walnut. So since you can't get a P or a walnut, you're left with just rows in singular.
Mm-hmm.
And from there, you can figure out, okay, now do I need more rows or singular? And that's where it ends up being that both of those work out together.
Okay.
And then you can do the same thing for the next one. Essentially, you know, they have to have recessive P's.
So this one for D.
For C.
Oh, for C.
Yep. So right above it, yeah.
So you got 1 rows, 1.
1-to-1 rows to single. So you have to have recessive P's again, because that cuts out your walnut and P. And then again, we need the big R, little r, but we also need recessive on both of them. So I got a heterozygous R, homozygous P, times a homozygous recessive for both of those. And they ended up coming out to be 1/2 and 1/2. So you get a 1-to-1 ratio on them all. What did you figure out? What did you come up with your answer then?
I don't know. I did this like a couple days ago.
Okay.
Just trying to figure
Well, it
out.
looks like you've got the same answer here.
Yeah.
Yeah.
So RP, RP, RP. I just not understanding why, but
What you put where?
yeah, why
Okay.
I did that. Oh, that's
Or
weird.
you started P's up here and then you dropped your P's everywhere.
Yeah.
So yeah, I don't know.
I don't know. I'll figure it out later.
And then the last one, I wasn't 100% positive on that one either. But I thought if you did heterozygous on all of them, it ended up being right. And again, I could be wrong there, but
Heterozygous on all of them?
oh no, that's not going to work because then I would end up getting a single. Just with the odds, it would be a single.
Yeah.
So yeah, that's not going to work.
You got big R space, big P.
So one of those has to be
You
big
got
R.
3 of those. And then you got big R, little p, little p.
Yep.
Okay, so you have to figure out what is needed. You need a little p.
Yep.
And does this matter?
Well, it's going to be because if I just looking at mine where I have both of those being heterozygous, it's going to come out that I will get. You'll end up getting a single because the little r's will eventually get together and the little p's. So if you do both of those as big R and go over, it means you're always going to have a big R. So you're either stuck with walnut or rose now based on just the R's, and doing both of those heterozygous. Eventually those little P's will get together, which will give you a rose, but also the big P's could get together, or the big P and a little p, which will end up giving you a walnut.
Okay.
So I guess what I'm kind of doing is the FOIL method a little bit. Of just figuring, okay, that would give me, doing this and kind of rotating around.
So you're working backwards.
Essentially, yeah.
Okay.
And that's just what kind of made sense in my mind, I guess.
Yeah.
And so figuring out, well, how do I cut out not getting single? Well, I can't have all recessives, which is where I made my first mistake. But then how do I cut out my...
I think this is right. The big R, big R.
Yeah.
Okay.
And it looks like that's what you ended up
Yeah,
getting
that's what I had
too.
too.
Okay. This one confused me for a while.
3.
So, how did you explain the inheritance of the coat color?
So you get, I just thought of the flower. So you've got a gold yellow coat,
Okay.
you've got a brown coat, and then you've got a white coat.
Okay.
And so so you mix a palomino times a palomino.
Mm-hmm.
Somehow you got something other than that.
Then, yeah.
Which means there's something going on with
that means the genes are mixing in a way that doesn't just go straight across.
Exactly. It's not all palominos, which is C little c.
But then you also go down to, like if you do a chestnut and a cremello, that last one, you only get palomino. And you do, so with chestnuts together, you only get chestnuts. With cremellos, you only get cremellos. But then if you mix the two, you get palominos. So I didn't necessarily, they're not incomplete dominant. I think that if you have a heterozygote, it becomes a palomino. And so a heterozygote is going to be something different than a dominant or a recessive.
Well, yeah, because it would be just a mix of the two. It's like having a pink flower.
Okay. So I guess the part I was thinking is you have cremellas which are white and brown, which I guess that would make yellow. So yeah, I guess you're right.
So this would be your red flower. That'd be your white flower.
And this is your
Mixed
pink.
between is a pink.
Yeah, you're right. So it would be an incomplete dominance then. And then did you just get the kind of that same thing? I don't know what the second one.
Palomino would be big, little. So yeah.
Yeah, big, little, and then chestnut is dominant, and then recessive.
Yeah.
Okay, yeah. I don't like doing C's for those things because big C's and little C's end up looking together.
Yeah.
So I did H's. But so then I got the first one is codominant. Because wouldn't I and B both be codominant alleles?
Enzyme. It's
no, this
asking
is
for the enzyme, yeah.
Named. Okay. What did you get by chance?
Glycosyltransferase.
Okay. And then did you get galactose?
Yeah.
Is what it puts on there.
Yeah.
Okay. Then the next one, over dominance.
Mm-hmm.
Incomplete penetrance.
Yep. Epistasis.
Yep. PKU.
Yeah.
The
phenylketonuria.
Yeah.
Yeah.
So then I couldn't figure out what the Mantrix trait displayed. I mean, it was a lethal trait. I got that. But is that the type of inheritance?
Uh-huh.
It's just lethal inheritance?
Yep.
Okay.
It's lethal for both.
I wasn't sure if that was a lethal inheritance or if there was a different name for that. So then the next one.
Okay, these ones I didn't.
Yeah. So, and I don't know anything about the maternal still. I've never really heard of it, that maternal dominance and stuff.
Yeah.
But since it says the female snails, 30% of them are DD, so that would mean that they're dextral genotype. 30% are heterozygous, which means they're still dextral. And then 40% of them are sinistral.
Which is recessive, which is 40.
Yep. And so
Okay.
then it says they're allowed to randomly mate with 50% of snails that are heterozygote and 50% that are homozygous recessive. And I thought that since the maternal, it always just follows the same as the mother, wouldn't it just not matter who they mated with?
Females, males.
Males, you have 50% that are heterozygous
And then,
and 50% homozygous recessive.
okay.
So little d. And so my understanding of that was that it honestly didn't matter what their phenotype was because it just follows the female.
Mhm.
So where these are both going to be the dextral because it's the dominant, you get 60% dextral and 40% sinistral. Yeah, which I ended up adding my numbers wrong again, but at least that was my understanding of the whole maternal phenotypes.
That's 5. Okay, that's 30.
Yeah, and that's what you've written there at least.
60, 40.
Yeah.
Okay. Dextral. Okay, and then GH.
So I did on this one. So these are the ones where they can mix together, that you can have a green and a white leaf. So I took what they told us here. So 40%. So 4 out of 10 of the female plants are green. So we got female green, 4 out of 10. And then 60% of them are female white. So 6 out of 10. And then they're able to randomly mate with 50% males that are green and 50 that are white.
Okay.
And then I just went, so if 4 of these females mate with these males, I'm going to end up with 4 out of 20 that are green, and then but they could also mate here, and it would give you another 4 out of 20 that are green white because of those two mixing. But then if this one mixes with this one, you get another 4 out of, or you get 6 out of 20 on this one that are green white, and then if these two mate together, you get 6 out of 20 that are white. And so that gives you the correlating what's green white and what's green and white.
So this mixes with
This one, so if any of these mix here, the likelihood is that they're going to give off a 4 out of 10 green or 4 out of 20 green plants, because we don't really care about what the gender is. We just care that this female is going to mate with a male, one of these two, and this one's going to mate with one of those two as well.
okay. Hold on. So 1/2 is the same thing as 5/10.
Yeah.
So it'd be 9/20.
1/2 would be the same as 5/10, but you don't need the common denominator when you're multiplying. You just multiply straight across. So the 1 times the 4 over 2 times 10.
Oh,
So it's 4/20.
gotcha.
Yeah. So you're doing the same as if you had a big Punnett square that you just multiplied across on.
Okay.
So I ended up with 20% that are green. 50% of them are the mixture of the green and white, and then 30% of them will be white.
Okay. Gotcha.
And this last one took me a little while too. So the first one,
So this is just something's more dominant than the rest.
yeah.
Okay.
So the first one I got big B, little BS, the Sempia or something,
Big B, little.
and the Sempia. I just did it as big B is the black, and then little B's with different superscripts were the different colors here. That's how I ended up doing it, at least.
Okay.
Just so that everything was still in the same gene. But so I got
Okay.
a black and a Sempia
Okay.
times a
And
black and a Sempia. Is how I ended up getting the first one, I think. So that would give you a black there. That one won't work, because then I'd get 3 blacks here. And that was the one that took me the longest. But
So
so if I want 50% black, this one will be black automatically.
black sepia times sepia cream. Black sepia, sepia cream. Black sepia, sepia sepia.
Hey buddy, how you doing?
Black cream, sepia cream, which would give you 50% each.
Yeah. Could you also do it with a black Sempia and Sempia?
Black sepia, sepia sepia. So
Because then
black
those,
sepia,
because the black's not going to change, and then you just have
black
Sempia.
sepia.
So there's actually
Yeah,
there's a different option there.
Yep.
So you could do either one, where you have a black rabbit and a Sempia rabbit that's homozygous, or a black with a Sempia rabbit that's heterozygous with either C or the white,
Yeah,
even. As long as it's just less than that Sempia.
exactly. Yeah.
Yeah. Then the second one, let's see where I put that one.
So 75% sepia, 25% cream offspring.
So this one I got Sempia cream for both of them. Ended up working out for you, and both of those are going to be Sempia colored. Right.
Sepia.
No, I can't. I'll be down for blues tomorrow though. It's at 7. No, at 9. No, I'm married. It's in the morning. I don't know when the wedding is, but I'm going to the reception. So. Well, they invited me to. So.
Well, probably.
No, yeah, you can't do that.
Yeah.
Yeah,
So that's where you could have sepia white or sepia cream togethers.
Sepia white, sepia white.
Well, but you want one that's cream.
I mean,
So sepia cream,
Oh.
sepia cream would work for you.
yeah. Okay.
But you could do one sepia white and one sepia cream because the cream
It
is
would-
still more dominant than the white is.
Yeah.
And so again, it works either way there, but they both need to be sepia colored.
Okay.
Their phenotype needs to be that. And C, I got that we need a black white with a sepia white to get the answer right.
Black, white, and sepia white. Yep.
Yeah. And then they'd be black and a sepia rabbit. And the last one I got black, white, black, white.
Yep.
Okay. It's just a normal heterozygous cross there, so both of them would be black, but you'd have the one ugly duckling.
Yeah.
Cool.
Alright. Sounds good. That worked.
Perfect. You want to send me that link again?
Yeah.